So in this example, we're going to talk about the energy line and the hydraulic grade line. Okay, and the idea behind this is that we want to be able to measure different aspects of flow. So if we're going to start out with Bernoulli's equation, and then we're going to divide by the specific weight. So we've got Bernoulli's equation, P1 plus 1/2 rho V1 squared plus gamma Z1 is equal to a constant along a specific streamline. And we're going to divide by the specific weight. So gamma is equal to rho times G. Okay. And that's going to leave us with this equation. So we're going to have the pressure divided by the specific weight. Then we're going to have V squared over 2G plus Z, and that's going to equal another constant. We're going to call that H, and H is the total head. Okay, and the idea behind this is that it gives you an idea of the height in a measurement device that this would generate. Each of these terms, we know that they come from energy terms, but when we express Bernoulli's equation this way, this becomes the pressure head. The second term becomes the velocity head. And then the last term becomes the elevation head. And the idea is you can see generally what's contributing to the overall energy of the system. Okay, and we can measure this using a pitot tube. So remember when we have the pitot tube basically brings the flow to a stagnation point right in front of the entrance. And what it's doing there is it's taking all of those different energy terms and converting it into pressure. And that pressure is what basically maintains the level of the liquid within the pitot tube. Okay. So if we ignore the velocity term, then basically our pressure head plus our elevation head is known as the piezometric head. Now this can be measured by a piezometric tap. So the piezometric tap is basically if you have some sort of pipe and you have just an entrance, then you're not stopping the water, so none of that kinetic energy is being converted, stopping the liquid, so none of that kinetic energy is being converted into pressure. So the elevation and the pressure are the only things that are being taken into account here. Okay, so if we have a pipe, for instance, that has a little bit of a slope, we can stick a pitot tube in here, and then right next to it we can stick a tap. Okay, and we're going to do the same thing a little bit further up the pipe. We're going to basically put a pitot tube here, and then another tap here. Okay, and if we're looking at, I'm going to make my pitot tube a little bit taller on this one here. Okay, if we're looking at the measurement in the pitot tube, since it's the same flow, we're assuming that the energy is being held constant. Okay, so what we would expect to see is that this line here is the same in both pitot tubes. Okay, and that line is called the energy level, or energy line, either one. Okay, and that represents the total energy in the system because that takes into account all three of the terms in Bernoulli's equation. Now, if we look at the piezometric taps, then what we're going to see is something a little bit different. So initially at the lower elevation, we'll probably see something like this. Okay, and this red line here represents the hydraulic grade line. Okay, so that's basically the energy that is just the pressure and the elevation or height, if you want to think of it that way. And the difference between these two lines is going to be v squared over 2g. Okay, so if I measure here, this is going to be a smaller difference than if I measure here, for instance. So this value is not constant if we have a pipe that's tipped, for instance. Okay, but the difference in height between the two lines, and again, you're going to measure the blue line with the pitot tubes. So we'll just write this down here. These are going to measure the blue line, so they'll give us the total energy. And this is going to measure the red line, okay, which is going to give us the piezometric energy. Okay. All right, so I just wanted to run through a couple of examples and talk about them real quick. What if we have a tank of water here, and we have a pipe that's coming off, and then eventually that pipe narrows, okay? And we've got this kind of no change in elevation, for instance, in this one, okay? The total energy is basically going to be wherever this liquid is, okay? So this is our energy line, okay? Now, what happens is, remember that the difference between the hydraulic grade line and the energy line tells us how much kinetic energy it has. And so when we're at the tank of water, well, the hydraulic grade line is going to be the same as that energy line, right? And then when we get into this section, we're going to see an increase in velocity, so the hydraulic grade line is going to kind of drop a little bit from the energy line. And in this section, because if we remember our continuity equation, a smaller area corresponds to a higher velocity, we're going to see another drop in that hydraulic grade line. Okay, and again, in both cases, this represents v squared over 2g. So what this tells us is that we have a higher velocity over on the right here. Okay, so if we use these different instruments, we can basically ascertain how fast the flow is going. Another thing that's useful to know is that if we have a pipe, for instance, that has a line coming off of it, and that line is moving around, or actually not necessarily moving around, but has different heights, that's going to change the pressure within the line, for instance. So we've got a flow that's heading down, but let's just assume that the velocity is constant here. Okay. So if we look again, our total energy is going to be at some level like this, right? And then we're going to have our hydraulic grade line. So our hydraulic grade line at the tank is going to be the same, and then it's going to pick up some velocity, which means our grade line is going to diverge and it's going to drop, okay? And what we can see is that at some points, because this tube is kind of waving around, we're going to be at some points above the hydraulic grade line, and at some points our pipe will be below, because that's the red one, okay? So if the pipe is above the hydraulic grade line, then that tells us that the pressure in that is going to be less than 1 atmosphere. Okay, and what that means is that if we were to punch a hole, for instance, right here in this pipe, then what's going to happen is the pressure will not be larger than the atmosphere, so it's actually going to result in air being pushed in from the atmospheric pressure outside, and so we're going to end up with air leaking into the pipe. Okay. Now below, so when we're in this section here, if we're below that line, then basically our pressure is going to be greater than 1 atmosphere. And what that means is that if we punch a hole somewhere in the line, we're actually going to, that pressure inside the pipe is going to be greater than what's outside, and it's going to force liquid from inside the pipe out through that hole. Okay, so in this case, we're going to have a loss of liquid from the pipe. Liquid, or I should say fluid, because it could be a gas too. Okay, so it's very important to think about where is the hydraulic grade line and how does that compare with the placement of the pipe. Why is this important? Well, in some cases, having, if you're going to have a leak with, for instance, oxygen might be very bad if you've got a fluid that's easily combustible, okay? So in that case, you definitely want to make sure that whatever line you're using to move that fluid out of the tank is definitely not above that hydraulic grade line. Conversely, if you have something that it doesn't really matter if a little bit of oxygen gets in it or something like that, or nitrogen, it's not dangerous, that sort of thing, then you're going to want to be, or you can get away with having something that's under a lower pressure. This is the case you see more often because a lot of things like water or oil will end up being underground, things like that. And that can be a problem because if it's underground, then you're going to probably be below that hydraulic grade line. And, like with gas, you definitely don't want air to be getting into gasoline or something like that because it's highly combustible. And if you introduce oxygen and heat it up, you could end up overcoming whatever energy you need to initiate combustion. So they will put these below the ground, but then you have the opposite problem where, well, if it does start leaking, you'll have things like gasoline or petroleum leaking into the ground, and that can affect things like the groundwater or the safety of the area. There's a pretty famous area in California, starts with an A, but it's a beach area, and they literally had to dig up and clean all the sand in this beach area because so much petroleum had leaked into it. So that's something to think about when you're designing systems that might be transporting fluids.